Hi everybody, welcome back. This is lesson 14 from Unit 1. It should be one of our final lessons of Unit 1. And in this lesson, we're going to learn how to, sorry about that, Hunter. We're going to learn how to calculate energy changes while heating and while in phase changes, okay? So if we're calculating heat energy, and that's the kind of energy that we're always calculating, it's heat energy. There are three equations for this in our reference tables. You can find them on reference table T, as in Thomas, and I just want to show you them real quick. If they ask you or give you heat, what you should see here on table T, hopefully you can see that, is that there are three equations to calculate heat. Students always have a hard time knowing which equation to use. And so I classify these as type 1 and type 2 equations. Type 1 equations you use when the temperature is changing, okay? When the temperature is changing, you're going to use the type 1 equation. And that is the one that says Q equals M times C times delta T. And I want to define these variables real quick for you. Q is heat, and when you calculate it or you plug it into this equation, the unit for that should be joules, capital J. Okay? M is mass, and you can identify mass by its unit, which is the gram. Delta T is the change in temperature. And it is the final temperature of your sample minus your initial temperature. Okay? Final, IN meaning initial. Okay, so T final minus T initial, that's your change in temperature. And there's one, and you can recognize temperature, it could either be in K for Kelvin or in degrees Celsius. It really doesn't matter, but both temperatures have to be in the same unit. And then finally, we have C, which is specific heat capacity. And the values for, or the units for specific heat capacity are joules per, let me just make this, joules per grams degrees Celsius. I'm going to write it over here because I know that was kind of off the screen. The units are joules per gram degrees Celsius, or they could be joules per gram Kelvin. Now, just a word about specific heat capacity. It is officially defined as the energy it takes to raise 1 gram of a substance 1 degree Celsius. So you're raising the temperature of a gram of, say, water 1 degree Celsius. And it's a constant for a given substance. So for water, you'll find it here in Table B. It takes 4.18 joules of energy to raise 1 gram of liquid water 1 degree Celsius, or 1 Kelvin. Doesn't matter, either way, it's the same deal. Okay? So that's our specific heat capacity. Let me show you how we use this one in some type 1 problems. Example number 1. The specific heat of aluminum is 0.9 joules per gram degrees Celsius. A. Calculate the energy needed to raise the temperature of a 0.00850 block of aluminum from 22.8 to 94.6. So, let's, every time you see a number, stop and identify what it is. The specific heat of aluminum is 0.900 joules per gram degrees Celsius. They call that specific heat. The units clue you in that that's specific heat. That's our capital C in our equation. The next number I see is right here. The unit is gram. That is our mass in our equation. We're raising the temperature from 22.8, that's our initial temperature, to 94.6, that's our final temperature. And whenever you have the final and the initial temperature, you can get the temperature change. So right away, I'm going to subtract these. 94.6, excuse me, 94.6 minus 22.8 to get my delta T, my change in temperature in degrees Celsius. So this is why you need a calculator for this class, everybody. 94.6 minus 22.8 should give us 71.8 degrees Celsius. So I think I've identified all the numbers that were given in the question. Now I want to know what the heck they want. So I look for what they're asking for. And what it tells me to do, I circle, calculate the energy. That's what they want to know. Energy is heat. Heat is Q. So that's my Q in my question. Since the temperature is changing, I am going to use the equation. Q equals M times C times delta T. And now I just plug in my variables and solve for Q. My mass is 0.00850. My specific heat capacity, or C, is 0.900. And my change in temperature is 71.8. All I do now is multiply those to get my answer. And you should come up with, let me just make sure I did it right, 0.0085 times 0.9 times 71.8. You should come up with 0.54927. And you found Q, and Q's units are joules. That is your final answer. Okay? Let's do another one. Let's do letter B. Now, letter B is still part of this question, so it's still aluminum. So we have the specific heat capacity for aluminum. It takes 10,000 J. Stop. It's a number. Who has the units J in the equation? Who is measured in joules? Hopefully you're right. You know this is your Q. Okay? Q is your joules. Well, let me put a box around that. Okay? So this time they gave us Q. We're not solving for Q. Of heat energy to heat a sample of pure aluminum 20 degrees Celsius. Obviously, degrees Celsius, that is the temperature. When they give us a temperature, it could be the starting temperature, which we call TI, the ending temperature, which we call TF, or the final temperature. So sorry about that. They have a temperature there. It's 20 degrees Celsius. When they give us a temperature, it can either be TI, the starting temperature, TF, the ending temperature, or it could be the change. They may not be telling us it started at 20 or ended at 20. They may just be telling us it changed by 20. So you have to read it carefully to figure out if it's a starting, ending, or if it's the change. It takes 10,000 joules of energy to heat a sample of pure aluminum 20 degrees Celsius. It's not starting at 20. It's not ending at 20. That is how much it changed by. So this time they're only giving us the one temperature, right? That is our change in temperature. That's all the numbers. We have our C from up here, our delta T, and our Q. What the heck do they want? Calculate the mass. So they're asking us for the mass of this sample. Since temperature is changing, we use the Q equals M times C times delta T equation. But this time they've given us Q. 10,000 equals M, we don't know that, times our C, which is 0.900 because it's aluminum, times our delta T, which is 20. So we're going to mathematically solve for our M. To mathematically solve for our M, we're going to combine our like variables here. We're going to multiply 0.9 times 20, and we're going to get 18M equals 10,000. I'll continue up over here to get m by itself, you'll divide both sides by 18. So we'll have 10,000 divided by 18 equals 18m divided by 18. So your mass is going to equal 10,000 then divided by 18, which if we round to the nearest whole number is 556. The unit for this, its mass, is grams. All right, one more. I think, do we have one more or two more? I'm going to do, let's do one more. It takes 78.2 joules to raise the temperature of 45.6 grams of lead by 13.3 degrees Celsius. Calculate the specific heat capacity of lead. So every time I see a number, I want to stop and identify what it is in my formula. And what I use to identify it is the unit that comes after it. 78.2 joules. Joules is heat. Heat is measured or represented with the letter Q in our equation. To raise the temperature of 45.6 grams. 45.6 grams. Grams is our unit of mass, and we represent that with an M in our equation. 13.3 degrees Celsius. Degrees Celsius is a unit of, now this isn't capital C in the equation. This is the unit degrees Celsius, which is a temperature. Is it the starting, the ending, or the change? Are you starting at 13.3? Are you ending at 13.3? Or did it change by 13.3? That's your delta T. That's all the numbers. What do they want to know? Calculate the specific heat capacity. Specific heat capacity is capital C in our equation. It always has the units, remember, joules per gram degrees Celsius. So we're going to solve our equation. Q equals M times C times delta T. We're going to solve our equation for capital C, specific heat capacity. It's a little bit confusing because this is degrees C, which is unit of temperature. But that isn't C in our equation. C just stands for capacity, specific heat capacity. So plug in your Q, what you know, 78.2. Plug in your M, 45.6. We don't know our C. Plug in our temperature change, 13.3. So again, combine the variables by multiplying 45.6 times 13.3. You get 78.2 equals 606.48 C. Divide this side by 606.48 and divide this side by 606.48. And I'll just put my answer over here, 78.2 divided by 606.48. You should know it cancels to 1 on this side, so C equals 0.129. And the units would be joules over gram degrees Celsius, because those are the units for specific heat capacity. Okay? For tomorrow, I would like you, in your notes please, to identify every number in this next question. So write down the number, write down the variable or the letter that it represents in the equation. If you think you can go ahead and solve it, then try. I'll be really impressed. Maybe we'll have to give you some bonus points. If not, we'll pick up here on Friday with this type of problem, okay? So you're writing this in your notes. You're circling and identifying all your numbers. What letters do they represent in the equation? You identify your unknown. What the heck do they want us to solve for? And tomorrow we'll start with this in class. Have a great night. Bye-bye.